We have a very technical session here. The title is IEEE's Wireless Ethernet, but as Al Petrick in the last session mentioned, IEEE actually spurned technology into all the mainstream wireless standards, including 4G now. So I'm going to cover a little bit beyond IEEE, but we'll certainly focus on the IEEE technologies here. So we've come a long way from the early to mid-'70s when we saw our first clunky cell phones. Essentially, we started with what's now we can call 1G. Back then it wasn't called 1G. And progressed to GSM, CDMA, 2G technologies that still dominate voice communications today, to 3G that's just getting deployed about 10 years after the standards have been released. And what's happened between 3G and 4G is IEEE. And IEEE came in and started with Wi-Fi and essentially changed the world of wireless communications as we know it. And what we will see in this session is how Wi-Fi and later WiMAX have introduced a whole bunch of new technologies that are key today for 4G. And 4G has essentially followed in the footsteps as we go from OFDM to OFDMA, Wi-Fi to WiMAX to LTE. So we're going to look at how all that happened and what it all means in terms of standards and performance. So I thought I'd start by decoding some of the buzzwords that we commonly see before diving into, obviously, standards is a lot of technology and politics. All of these wireless technologies, it's not always that the best technologies win. But we're going to start in the technical realm and then touch a little bit on the politics of it all and why some technologies are more successful than others and what to expect in the future. So some of these are all of the different modulation and access schemes in use today. TDMA is the early time domain multiple access, basically used in GSM today and earlier in the AMS technology. And CDMA is mostly what we use here in the U.S. for cellular voice communications. And there are quite a number of variants of CDMA, and it evolved into 3G technologies like WCDMA and CDMA 2000 are now 3G data technologies. SDMA is something new, and it's all related. These four are somewhat related. As we start running out of spectrum and time, how do we fit more data in? We start doing spatial multiplexing. We transmit different data in different slots of space. So SDMA is related to MIMO and beamforming. We're going to cover that. FDMA, frequency division multiple access, started out in some satellites, not used in mainstream, but it evolved into OFDM and OFDMA. So let's take a look at what all of these things are. Now, TDMA is essentially time slots. CDMA, some people find it more difficult to understand. Now, this slide was borrowed from Ralph Turner, who's also presenting here, and came from Suresh Goyal and Rich Howard originally. So the way to explain CDMA is you have a whole bunch of transmissions happening simultaneously in the air, and only by knowing the code can you make out the stream or the conversation, the voice conversation of interest. So that's essentially a non-technical explanation of CDMA. If you want technology, it's a lot of math. But it's all in the coding. Okay, so FDMA is simply frequency channels. It's a fancy name, frequency division multiple access, of having different transmissions in different channels. TDMA is basically when you have different users using different slots in time, and that's your typical GSM. OFDM consists of multiple carriers, orthogonal frequency domain modulation, and essentially divides up the transmission. Instead of sending very fast symbols or on the wire, it makes symbols slower, but it transmits them simultaneously on multiple carriers. And that's the way that we overcome reflections. When you have long symbols, we can wait until you decode the symbol for the reflections to settle. And that was essentially the innovation behind OFDM, happened in Wi-Fi. 802.11a and G use OFDM first time commercially. So what's FDMA versus OFDMA? Now in OFDMA, OFDMA is not just a modulation scheme, it's actually an access scheme. It stands for orthogonal frequency multiple access, not just modulation. And this was a step essentially from 802.11 to 802.16, where we said, okay, so we have multiple frequency carriers carrying different data, so why not just divide them up into different users? Why is this better than FDMA? It was because when we basically have different channels, there are always guard bands between channels, and we don't use the spectrum efficiently. When you go to OFDMA, the carriers are orthogonal and they don't interfere with each other. They have a special relationship, so you can squeeze them right next to each other and use the spectrum a lot more efficiently. So OFDMA essentially is the most efficient OFDM-based technology that's used by WiMAX and LTE and probably all the future standards that need to be efficient on the air. So to further elaborate on this, so you have fixed OFDMA, where you just give different users different subsets of carriers. But you can also have dynamic FDMA, where if, let's say, some users are silent for a period of time, their carriers get allocated to other users. And there's a complex scheduling problem, but essentially this is what's used in WiMAX and LTE today. A base station decides which users get which carriers and what time slots. So it's a kind of a combination of TDMA and FDMA together. Another concept that's important to introduce is that of TDD and FDD. TDD is time division duplex, and FDD is frequency division duplex. Traditionally, 3G, cellular technologies and 2G have been allocated spectrum, uplink and downlink spectrum, so that you would have one channel for a station to communicate to the base station and a different frequency channel from the base station to go downlink. And the spectrum is allocated as pairs of uplink, downlink spectrum. For Wi-Fi and WiMAX, those guys came in a little later on this scene and said, well, why do we need two channels? When you have fixed allocated channels, it's not very efficient if you have, let's say, more downlink traffic than uplink traffic, because it's common for web browsing. It's much more efficient to do the scheduling and allocation all in time domain in TDD. So the more modern technologies are using TDD. However, and that's where WiMAX started out. However, they quickly found out that a lot of the spectrum is allocated in pairs, and that in order to be successful, they have to do FDD. So they went back in the future release to support FDD. LTE started out with just FDD, and they quickly found out that they also need to do TDD, so they kind of moved. And so both technologies now support both. So this may be a little bit complicated, but essentially what happens in TDD transmission is there is a time. This is time. And there is a downlink transmission from a base station. And there is, in the beginning of each transmission, there is a kind of a map that tells each station which slot it has to transmit uplink. Then it's followed by an uplink burst. And different stations can be transmitting on different sets of OFDM carriers. And this is the most efficient way to use the time. So station can request more or less bandwidth. If you're just doing voice, you don't need a lot of carriers. If you're doing a lot of data, you can get allocation. And that's the power of something like WiMAX and LTE over Wi-Fi. Wi-Fi is a very simple technology, straight OFDM. You cannot do fancy stuff like that. With FDD, and most of FDD technologies are now half duplex, you do similar things, but you would transmit simultaneously on uplink frequencies and downlink frequencies. So you would still schedule, but let's say the scheduling is announced in the downlink frame, and then the uplink for that announcement follows, and so forth. But it could be also full duplex. FDD does support full duplex. ITU, International Telecommunications Union, has allocated some frequency bands. And there's a lot of detail here as far as TDD is simple. There is one channel. For FDD, there's half duplex, full duplex. You have to look at the paired channels, and there are large tables and standards for where the channels are allocated in these rough bands. But you can see that Wi-Fi fits in between here, 2.4 Wi-Fi, and then above 3650 to 3700 is lightly licensed band we'll talk about later, and then at 5.8 gigahertz we also have Wi-Fi. So what is ITU? ITU is essentially, it's a UN standards organization, and ITU decides the framework of communications. ITU decides which technologies are 3G, which technologies are 4G. About a year and a half ago, ITU has blessed WiMAX as being 3G, and that was a big achievement for the WiMAX camp. Up until then, ITU has been European focused and has worked with European organizations like ETSI and 3GPP. So IMT 2000 is essentially what we use today. ITU defines a high-level framework. Yes?
So what was the criteria to determine WiMAX is 3G as opposed to 2G?
I am not privy, but I know it's more politics than technology. Essentially, it's they do have a data rate requirement. For example, this is the current framework has 30 megabits per second, and this is the 3G rate. So they had to meet some limits that were set, some mobility requirements for velocities at which this is supported, because 3G is essentially mobile technology. And we'll talk a little bit more about mobility and what it means in terms of technology and standards. So IMT Advanced is basically the next generation, supposed to be deployed in 2010, 2015, with data rates reaching 100 megabits per second for high mobility. So this is their basically a threshold for 4G. Advanced is essentially 4G, although 4G officially has not been defined by ITU or anybody. Although WiMAX and LTE both claim to be 4G technologies, that's just marketing for now. So data rates for nomadic networks like Wi-Fi are required to reach 1 gigabits per second. So today, .16, both .16 and .11 are working to meet the framework of ITU for IMT Advanced. International Mobile Telecommunications is what IMT stands for. And the work is going on. We'll review some of that. 802.16m is essentially the next generation WiMAX standard, and AC and AD are that 11 standards that will reach 1 gigabit per second. AC operates below 6 gigahertz, so in the traditional 2.4 and 5.8 gigahertz bands. And AD uses about 7 gigahertz of bandwidth up at 60 gigahertz. There's unlicensed spectrum there in order to reach these high speeds. And again, we'll look at that. So essentially, ITU sets the framework and sets these high-level requirements for throughput, mobility, and so forth. And then organizations like IEEE and 3GPP fill in the detailed standards and work with ITU for ITU to then bless these standards and designate them as 3G or 4G and so forth. Okay, so 3GPP. What's 3GPP? It works in parallel with IEEE, and they have a tendency to adapt a lot of the work that happens at the IEEE. IEEE tends to be ahead of 3GPP. So, for example, WiMAX has pioneered OFDMA. Wi-Fi has pioneered OFDM. LTE is using, it's mostly the same as WiMAX with OFDMA standard, and essentially the same scalability and channel width. They have pioneered some new techniques like single carrier, FDMA, which we'll look at. But for about 80% of the standard is the same. But the organization, the politics here work differently. 3GPP essentially has 6 regional standards group. In the USA, it's mostly ATIS. And if I wanted to go to attend 3GPP meetings and contribute to the standards, I'd have to join ATIS and be a delegate through ATIS. And then ITU can reference the regional standards that are translated by these groups. So it's a partnership project. Now, I don't know what they're going to do about 4G because they have basically locked themselves in. Europeans are not the best marketing people. 3GPP have never been good at marketing if you look at all their terms and names. But anyway, when they go to 4G, I don't know whether they're going to rename themselves or not, but they're essentially working on 4G now. So the way 3GPP works is a little different from IEEE. IEEE has evolved to have very stringent participation rules and voting rules, and for that reason, things can take standards can take a long time to be developed under IEEE, but they're very thorough. In 3GPP, there is a lot of influence that comes from the operators. NGMN is one of the organizations, Next Generation Mobile Networks, essentially organization of key operators, and they come together and define high-level requirements for 3GPP to then go off and do detailed standards. And then they have a testing organization like LSTI, LTE, SAE, Trial Initiative. And they define all the testing. Testing is defined in parallel with the standard. Testing is extremely important for the carriers because they own the cost of support when the technology goes in the field. So there's a lot more. IEEE traditionally has not worried about testing and certification. 3GPP, in contrast, does and have a committee dedicated from the start to the testing. Okay, so in summary, the Gs. The Gs are starting with, and the kind of the progressive peak rate, starting from 1 to, and there's all kinds of fine distinctions here for 3G, fractional 3G. Some of the 3G is CDMA based, and some of it is not CDMA. Well, the CDMA is mostly WCDMA or CDMA 2000 is what this HSPA, all the HSPA standards are. But now HSPA Plus is trying to compete with technologies that are now calling themselves 4G. And they have adapted MIMO. which we'll talk about later, what MIMO is, essentially multi-stream technology, to reach the data rates of 3G. Now, one of the issues is the carriers have invested into 3G, and it's just starting to get deployed. So they're trying to extend the useful life of 3G here with this increased data rate. 4G, WiMAX, and LTE have kind of equivalent data rates, and in the next generation we're going to be reaching 100 megabits per second or higher. Now, to put things in perspective, some of these are peak data rates, and statistically they are reached with very low probability. You have to have on the medium, you have to have almost perfect environment, be close to the base station to reach those peak rates. And for the most part, you're adapting. Wireless technology is all about rate adaptation and switching automatically to lower rates. And so for the most part, we will not see those kinds of rates out there. Okay. So 3GPP is playing here in the wide area networking world. But the world is small now, and it's starting to merge. You know, what we originally thought of as metropolitan area network or even LAN, local area network, is now starting to, I mean, the boundaries here are disappearing very quickly. So WiMAX started as a metro network. Now, obviously, they've introduced mobility, and that happened in 16E. And so they're definitely playing here in the WAN space as well. 802.22 started out as a regional area network to work in the country kind of setting with long range, and it was based on 16D. It's based on 16D OFDM. And its goal was to operate in the UHF spectrum at longer range where TV channels are not present. And 802.22 has interfaced with FCC and has been very influential in the white spaces legislation and rules that the FCC put out. And we'll talk a little bit more about that. And actually, I'm doing another session on white spaces on Thursday. So there'll be a lot more detail on that. Obviously, 802.11 has started, is known as a LAN technology, but now it is also possibly, you know, there's a new study group that's looking at white spaces, so it's hard to classify these things very neatly. And of course, personal area network are small networks, like Bluetooth, and Zigbee was also defined under 802.15. Now, 60 gigahertz is worth mentioning because that's the spectrum now. It started out for short-range communications, personal area network, because there's a lot of spectrum there, 7 gigahertz of available spectrum. 802.15.3c developed OFDM-based protocol to do short-range, kind of high-definition video transmissions in that spectrum. But now 802.11 has jumped in to satisfy the 1 gigabit per second throughput requirement, and they're also basing their work on what 802.15.3 has started. So these high transmission rates are going to come at the expense of distance, very likely. Okay, so history of .11. Obviously, .11 brought us OFDM and MIMO. You know, that's it started out, and it took a long time to do the original standard. It took almost 7 years before the standard was approved. It was a tiny group of people who basically looked at the cell phones and said, geez, you can do wireless cheap, you know, let's try and do wireless Ethernet. And then that's what it was called. And what's known as the Wi-Fi Alliance today was known as Wireless Ethernet Communications Alliance, WECA, at the time. And of course, 802.11, because wireless medium is so much more challenging than Ethernet medium, they've evolved away from Ethernet as the standard was developed during those years. It started out as 2 megabits per second, and I was using it back in the 90s, you know, back here in the mid-90s. I started using it at home, and of course there was no going back to wired. Once you can sit in front of the TV and do your email, that's it. And so because it was cheap and simple and it worked well enough, the technology was very successful, has evolved from its traditional 2 megabits per second to A, B, and G, now N at 64 megabits per second for each stream and multi-stream technology. And essentially we have Wi-Fi Alliance certification for N now. I'm actually working on their technology white paper for the released 802.11n certification. And they started Draft 2 certification back in 2006. And there's very little difference between Draft 2 and the release standard, but it took 3 years because of all the politics to basically get into the release. So DOT16 has evolved OFDM, the multi-carrier transmission, to OFDMA, basically to make it multiple access. So we think of Ethernet as collision detect multiple access. Now we have kind of modulation and access all together in this OFDMA concept. WiMAX started later than .6.11, and they looked originally at the fixed wireless, the work that was being done in fixed wireless up to 66 gigahertz. That was a very small market. Technology didn't go anywhere, but DOT16 picked it up and developed the 2004 fixed standard for wireless. And fixed, we're going to talk a little bit about what mobility means, but essentially it means that you can roam and that base stations can locate where the station is for the purpose of handoffs and emergency services and so forth. But it evolved basically under IEEE. IEEE has never been worried about mobility. And then DOT16 in 2005, they decided they were going to jump to this mobility requirement and address that to open up the markets even further. And that created the 2005 E standard. And the latest standard was just recently released earlier this year, DOT16 2009. They fixed up some things from 5E to that were actually broken with mobility, that it didn't work perfectly when it first got out. And they introduced FDD as well and fixed it up. Although it was in the standard, it wasn't quite deployed and didn't quite work. So a 2009 standard is essentially full FDD. The focus of DOT16 now is the next generation to meet the IMT advanced requirements. So if you look at what IEEE 802 Land-Man Standards Committee is doing, LMSC, this is all the data communication standards done under 802. It's mostly wireless stuff. And even 802.1 is now doing bridging. It's a higher layer bridging protocol. They're also doing bridging from wired to wireless for home communications to bring video, wireless video to the displays, for example. So wireless is basically the new frontier for data communications. TV white spaces is just starting. There are several study groups, and there's a lot of politics involved with white spaces because incumbents, people who run TV stations, TV broadcasters, are not thrilled to have two-way communications in their band. Traditional carriers may not be thrilled about having technology operating in unlicensed band where they paid a lot of money for their licenses. So this is a lot of politics here. 802.22 has been working, and most people think 802.22 is the standard for white spaces because they so closely worked with the FCC, but they have been kind of slow because of the participation of incumbents. And so the work is now shifting around the various groups at IEEE to make it move faster. So we'll talk a little bit about all of this. Under .11 itself, N is finishing up. There's a variety of alphabet soup here. The key standards are TG, AC, and AD. So what we talked about for the next generation N, AC is less than 6 gigahertz, so in the traditional 2.4 and 6 gigahertz and 5.8 gigahertz bands. and AD goes into the 60 gigahertz band. So there's a kind of a rate adaptation that happens, just like we change rates within a band. This essentially switches bands automatically when you need to go to 1 gigabit per second or thereabouts. The Wi-Fi Alliance is working with, it's not actually, there is a liaison, but IEEE is a very independent organization with its own rules, but the Wi-Fi Alliance mission is to certify, it's certification testing of all the .11 standards. So draft N versus legacy. So there is a tremendous step forward here. You can see the vast difference in throughput at different distances between legacy. This is just an example in 2.4 gigahertz band and the N products. I have personally tested this. This is the data that I got in a home environment. So you can see there's a huge step, and there's a good reason for that. And the reason for that is that N adopted the MIMO technology. So FDM and MIMO are now real keys to wireless communications. .11 pioneered both and established them, and then WiMAX and LTE have copied them because they work so well. So these are all the data rates. We talked about rate adaptation. So you can work anywhere from 1, 2 megabits per second. That's what we had in the mid-90s. And now commercial products are all the way up to 450 megabits per second. Now, how do we do this? So 11N, essentially, they did a variety of things to reach such high data rates. The easiest one is to double up the channel bandwidth. So we went from traditional 20 megahertz to 40 megahertz channel width. So that automatically doubles your throughput. But the more innovative thing is we introduce multiple streams, and that's a kind of a spatial multiplexing. We talked about, we're running out of, time slots, and we're running out of frequency channels. Those are all finite, so now what we're doing is we're dividing up the space. We'll talk a little bit about MIMO and how all this works, but if you can transmit multiple streams, you can do two things. First, you can, let's say if you have 2 streams, theoretically you can double the throughput, or if you have 3 streams, you can triple the throughput. In practice, it never works that way. You can triple the data rate, but throughput is a little bit less than double or triple. So today's product reached 3 streams, and we are expecting 4 streams to go up to 600 megabits per second. Operation is in 2.4 and 5 gigahertz band. There was a number of other innovations on top of just the data rate. The MAC layer was made much more efficient in 11N through aggregating frames and sending larger frames where appropriate. And they squeezed the space between frames through using short gap interval and so forth. So there was, N is really, when we had A, B, and G come out, those were really just physical layer extensions to the standard. The MAC stayed the same. With N, we changed both the MAC and the Phi to really make a huge, big step in throughput. So MIMO, you probably know how MIMO works, but essentially it requires multiple transmitters and multiple receivers in the radios that communicate. And the reason this has made such a big difference over a single transmitter receiver, the conventional one, is because really the signal bounces around. And in an environment, you have multiple paths for the signal. And if a receiver is sitting here, it sees the same signal from this access point, for example, reflected either from mobile reflectors or fixed reflectors. It sees multiple versions of these signals. So the traditional SISO, single input, single output, OFDM, your traditional 802.11a, B, and G, they basically had to battle all this stuff. They had to try to make some sense out of all these, the same signal coming and adding up in the air, the different delays, and the variety of clusters, and actually moving around in time. And what they did was they said, okay, well, if we can put multiple receivers, then we can use some very smart DSP to tune on each signal, and then we can combine them in an intelligent way. And it turned out that that works remarkably well. And also what it does is, you probably know about nulls. If you have two sine waves out of phase, they add together into no signal. So nulls happen commonly, they're statistically common in the wireless environment with a lot of reflections. Nulls are as known as fading. Sometimes you don't reach a perfect null. But if you have multiple transmitters, you can use the techniques like offsetting the signals in phase in such a way that if one of the antennas is received as a null, the other would be received as a peak. So all of these smart techniques that are being used, like transmit diversity like that and receive diversity with multiple receivers, it works very effectively. And so MIMO technologies are you usually see MIMO N by M. N usually stands for number of transmitters, M stands for the number of receivers. And in an indoor environment, you have different channel models that are being used than in the outdoor environment. In 11N developed its own models. There are 6 models, and they're called A through F models. For A's, B star is a small room, F is a very large space. But they model all these reflections in a room. So in the indoor environment, 802.11 define a 4x4 MIMO. That's a maximum because they see 4 paths statistically indoors. Today, the maximum implementations are reaching 3 streams, not 4. And the number of transmitters and receivers actually are not directly related to the number of streams because multiple transmitters can be used to form a single stream. So it gets a little bit into too much detail I don't want to get into now, but there could be up to 4 streams. That's what the PhDs tell us indoors, and probably more like 2 streams outdoors because there isn't as much multipath and not as much reflections. So in outdoor models, you have basically dominating 2 paths. So another important concept, we talked about SDMA, spatial division multiple access, and that's really being capitalized, not a little bit in the Wi-Fi space, but more so in the outdoor space where spectrum is really scarce. With the high order MIMO on the base station. So in WiMAX and LTE, what they're doing now, in Wi-Fi essentially simplistically is thinking 4x4. That means AP has 4 transmitters, 4 receivers, and a station has 4 transmitters, 4 receivers. Well, number one, that gets expensive. So when you go to a cell phone, how do you put 4 radios into a cell phone, and what's your battery life is going to be then? So handsets are simpler, but on the base station you can still put a high order of MIMO. You can put a 4x4, and now they have 6x6, which is common for WiMAX. And in the advanced standards, they're going to 8x8 MIMO on the base station. So how do they use that? And what they do is from the military, where they have these radar arrays with lots of antennas, where they use those antennas to form beams, the beam forming. They're using sophisticated techniques with these base stations with a lot of antennas to essentially form beams, but simultaneously they can form a kind of a shaped beam like that where they can direct energy to multiple stations at once. And this is where there's a lot of advancement going on now for WiMAX and LTE smart antennas. Beam forming, collaborative MIMO, where 2 stations can communicate at the same time. So it's all related to SDMA, dividing up the space. So the 802.11, you probably know a lot of the acronym soup here. The way it works is we started out with the standard. The first standard came out in '97. And then the working group is working on additions to the standard like A and B and N and I, ASIC security and so forth. So you get a lot of alphabet soups. Once in a while, they take all the amendments that are released and they put them into a new standard document. So you have these documents that are out now, 97, 99, and 2007. So there should be another one coming out with new amendments to it. So 802.11 started out as basically, it's sold in Staples, cheap technology, works great in the home. So it was a SOHO technology. But all of these amendments have evolved. The vendors started working on making it more enterprise grade and carrier grade. So what do you need in the enterprise? Well, you need to cover more space. So you need more than one access point. When you have more than one access point, you have roaming. If you have roaming, you need to do probably fast roaming if you want to talk on the phone or maintain your IP session. So 11R defined fast roaming. You also need management in the enterprise, 11K. So you have SNMP for Ethernet, but when you go to a Wi-Fi network, that's not sufficient. It's too slow. It's on the IP layer. It doesn't have information on all the wireless-related things like how busy is my IP, how loaded is it, how strong is my signal, and so forth. So radio resource management measurement allows stations and APs to find out, to query each other. You know, how busy are you? How many users do you have AP on you, and so forth. And 802.11v capitalizes on this information collected in the management information base to actually do management and maybe some load sharing and so forth. So 11R is fast transition. I'm going to go slightly fast here because we have to leave some time for questions. But essentially they define fast transition domains where authentication, which is what takes a lot of time when you're switching APs, is all that information is shared in the domain, and the transition can happen fast. Measurement, essentially network topology, devices power levels, and so forth. And V uses that information to manage, to distribute, to tell stations, and they introduce location, how do you locate the station where it is, geo coordinates and civic coordinates. And they attempted to manage the stations also for load sharing, to be able to tell the station which AP to associate with. That's still a little bit hard to control in the Wi-Fi world because the station decides in Wi-Fi which AP it's going to work on. But also introduce some of the more sophisticated power management technologies where the device can go to sleep if it just does voice packets once in a while and save on battery. Okay, so carrier grade. So what's the difference really between Wi-Fi and something like a GSM CDMA technology? Well, when you open up your cell phone, it discovers whether your service provider is there or whether it's on a partner network and all the billing is there, and that doesn't really exist in Wi-Fi. There's no emergency location services. So a lot of that work is being done in 11U, and there's a liaison to 3GPP. And this is a